Imagine the scene. After years of speculation, the world finally discovers that Tesla is about to launch an electric car for under $9,000 in 2026. It seems like an unlikely number, almost an April Fool's joke, but it's real, not just a tossed-up announcement. We're talking about something that promises to transform not only the automotive industry, but also the lives of millions of people who have always seen electric cars as a distant luxury. It's as if, suddenly, a dream that seemed exclusive to a select few is now within the reach of many. What's more, this isn't an experimental or limited-run model, but a production plan that foresees more than 2 million units on the road. The impact of this price is almost impossible to measure. If today we still see EVs costing well over $25,000, imagining a Tesla for a third of that is a true paradigm shift. It's like when a cell phone stopped being a luxury item and became available in everyone's pocket, changing habits, routines, and even the way we interact with the world. This Model 2 has the potential to repeat this revolution, only on wheels. Affordability has never been so palpable, and those who follow the industry have already realized that this announcement is not just a marketing ploy, but a game changer. Consider the impact on emerging markets, where electric cars are still seen as a distant prospect. In Brazil, for example, or even in several regions of Asia, a Tesla for under $9,000 could be the key to accelerating electrification in unprecedented ways. We're not just talking about technological innovation, but about inclusion, about allowing ordinary families to consider purchasing an EV for the first time. This breakdown of economic barriers will force competitors to rethink their strategies, and many are already beginning to wonder how they can compete in such a competitive environment. Tesla knows the key isn't just to lower the list price, but to maintain the quality that has gotten it this far. There's no point in offering an affordable car if it's fragile, unsafe, or has a ridiculous range. And it's precisely this balance between cost and performance that makes the 2026 announcement sound so unbelievable. It's not a cheap that ends up being expensive, but a vehicle that preserves the brand's essence while redefining the concept of affordability. Another intriguing point is the scale of the promised production. 2 million cars isn't a random number, but an indication of Tesla's absolute confidence in the capacity of its new assembly lines. This shows that this isn't just a niche project, but a global movement designed to flood the market and transform the presence of EVs on the streets. We can already imagine dealerships packed with curious customers, mile-long waiting lists, and a rush of reservations similar to what we've seen with other iconic launches from the company. Of course, many will raise their eyebrows and question whether it's really possible to deliver so much for so little. After all, the mathematics of the automotive industry have always been cruel to those who try to innovate too much to cut costs. But that's precisely the trick. Tesla isn't just reducing costs, it's completely rethinking the way it makes cars. The strategy isn't simply to cut costs, but to reinvent, and that's the detail that can make all the difference. The automotive industry has always carried a historical burden that now seems outdated. The production method that dominates today originated at the beginning of the last century, and, even with adaptations, remains a fragmented, slow, and expensive process. A typical car, whether combustion-powered or electric, comprises around 30,000 different components, each with its own supply, inspection, and assembly chain. The very idea seems like an organized mess, but when something goes wrong, the entire system grinds to a halt. It's no exaggeration to say that complexity has become the #1 enemy of efficiency. This model requires more than 20 hours of direct human labor to assemble each vehicle, not counting the time spent in outsourced factories producing specific parts. With each delay in a brake part or a simple electronic module, an entire assembly line can grind to a halt. This domino effect generates enormous costs that are inevitably passed on to the consumer. It's as if the car leaves the factory already carrying a hidden debt. which the buyer pays in the final price. In electric vehicles, the challenge is even greater. In addition to the traditional infrastructure, there's the complexity of batteries and cooling systems. The battery pack alone, on average, costs thousands of dollars and represents a significant portion of the car's value. In 2024, the average price per kilowatt-hour was still around $130, meaning that a compact car with a 50 kilowatt-hour battery already costs $6,500 in stored energy alone. This is before even considering labor, margins, and onboard electronics. Now, imagine all of this happening inside factories that, in many ways, still resemble those of the 1980s. Noisy machines molding sheet metal, endless conveyor belts, and workers repeating screw-tightening movements thousands of times a day. It's a scenario that, even with advances in automation, still maintains its antiquated essence. A cumbersome, sequential process, extremely vulnerable to failure. This outdated structure also creates barriers to innovation. Whenever a company considers changing a design detail, it has to review a huge list of suppliers, deadlines, and assembly standards. This means less flexibility, less speed to adapt, and, most importantly, more money burned. The result is that, in 2026, much of the industry still manufactures cars as if it were hostage to an old, complicated instruction manual. It's curious to note that, despite the market's talk of the future and electrification, the core production processes are still looking in the rearview mirror. The process that worked for combustion vehicles, with engines packed with moving parts and auxiliary systems, makes no sense when it comes to electric cars, which could be much simpler. But tradition prevails, and brands have been slow to understand that insisting on complexity runs counter to accessibility. The secret Tesla is implementing seems simple, but it changes everything. Instead of assembling the car from hundreds of stamped, welded, and fitted parts one by one, the company decided to use Giga castings, enormous casting machines capable of molding entire sections of the vehicle from a single piece. Imagine replacing a 100-part jigsaw puzzle with a solid block that's ready to go, without the need for seams or adjustments. This change eliminates points of failure, reduces material waste, and dramatically shortens production time. This concept of large-scale casting isn't just a natural evolution. It's almost a philosophical break with the past. Traditional automakers have always worked with small parts joined in sequence, believing this was the safest way to ensure flexibility. But Tesla understood that true flexibility comes from simplicity. With Giga presses, each car now has fewer weld points, fewer joints, and fewer areas subject to misalignment. And this, ultimately, means more predictable quality at a much lower cost. Another advantage is the direct impact on structural strength. A chassis built with large blocks of cast aluminum is not only more rigid, but also offers greater safety in collisions. Fewer joints means fewer weak points. This feature may sound overly technical, but in practice, it's what ensures the Model 2 is an affordable car without sacrificing driver and passenger protection. It's a detail that makes a difference for both buyers and regulators. Production efficiency also increases. By eliminating dozens of intermediate processes, Tesla reduces its dependence on external suppliers and can manufacture more in less time. This paves the way for its ambitious plan to reach 2 million units globally. Instead of waiting weeks for small components to be delivered, the factory now has a much leaner production line, where large sections arrive ready for assembly. This large-scale casting process also directly addresses environmental concerns. Producing fewer parts, with fewer steps, reduces not only costs, but also the carbon footprint of manufacturing. Less transport of parts, less welding, less energy spent on redundant processes. Ultimately, each car produced carries with it not only a lower price, but also a cleaner manufacturing history. Of course, there were plenty of critics who argued that casting such large parts would be a huge technical challenge. Indeed, maintaining precision on something of this scale is no simple task. Giga presses must apply thousands of tons of pressure and withstand extremely high temperatures without compromising quality. But Tesla has shown that by investing heavily in innovation, it's possible to transform a seemingly unfeasible idea into a standard that others will soon have to follow. When we think of an assembly line, the image that comes to mind is almost always the same: cars passing in a row, each station adding a part until the vehicle is complete. This model, created over a century ago, works, but it's fragile. All it takes is a broken robotic arm or a supplier delaying the delivery of a part to bring the entire line to a halt, creating a cascade effect that costs millions. Tesla looked at this system and decided to turn it all upside down, introducing the concept of modular and parallel production. Instead of following a linear flow, the Model 2 will be assembled in large, independent modules. The front chassis, structural battery pack, and rear assembly don't have to wait for each other. Each is produced, assembled, and tested separately, in parallel, with its own verification steps. When ready, they all meet at a central station, where the car is literally clicked together like a jigsaw puzzle. It sounds too simplistic to be realistic, but that's precisely where the genius lies. This change reduces total assembly time by more than 30%, and it's not just about numbers. With less dependency between steps, bottlenecks disappear. If one module is delayed, the others continue to move forward. The result is a much more resilient flow, almost immune to total shutdowns. This ensures production predictability, something that has always been a nightmare for the industry. After all, maintaining full inventories and idle factories because of a single part is a luxury no one can afford anymore. Another interesting effect is the possibility of decentralization. Because modules are independent, they can be produced in smaller factories closer to target markets and then shipped for final assembly. Imagine small gigafactories spread across strategic regions, reducing transportation costs and adapting production to local demand. This flexibility is something that competitors stuck in the linear model will be unlikely to replicate anytime soon. From an engineering perspective, modularity also brings advantages in quality control. Testing each section separately means detecting defects before they contaminate the entire vehicle. This reduces rework, increases reliability, and even lowers warranty costs. For the consumer, this translates into more reliable vehicles with a lower chance of problems in the first few years of use. And there's a curious side to this idea. It's very reminiscent of smartphone or computer assembly, where boards, camera modules, and batteries are manufactured and tested separately before being assembled into a single final product. Tesla, in a way, is applying the logic of consumer electronics to the automotive world, accelerating and simplifying processes in a way that seemed impossible just a few years ago. Until recently, talking about batteries was almost synonymous with high costs and technical limitations. They were treated as a simple pack of cells stored in a metal box, installed under the car, heavy and isolated from the rest of the structure. Tesla decided to break with this concept in the Model 2, transforming the battery into something much larger, an integral part of the body itself. This is where the so-called aluminum-lithium hybrid battery comes in, a breakthrough that combines chemical innovation with structural boldness. The first point of this change lies precisely in the material. By adding aluminum to the composition, Tesla can reduce its dependence on lithium, an expensive resource subject to market fluctuations. Furthermore, aluminum provides thermal stability benefits, making the pack less vulnerable to overheating and extending its lifespan. It's as if the material not only helps the wallet, but also increases user confidence, as users are less at risk of common battery problems. The next step was to reposition the pack's function. Instead of being a dead weight installed under the floor, it now becomes the floor itself. This eliminates extra supports, protective boxes, and even shock-absorbing structures, because the battery itself becomes part of the chassis. The gain is immediate. The car's overall weight drops by up to 15%, while simultaneously increasing rigidity. It's a classic case where fewer parts mean more performance and safety. Another striking detail is how this battery connects to the front and rear Giga castings. It integrates directly with these two cast parts, creating a single, rigid, and durable unit. This connection reduces welding points, eliminates vulnerable areas, and simplifies the assembly process. For the consumer, this translates into a lighter, more robust car and, interestingly, cheaper to repair in the event of an accident, as the structure is designed to absorb impacts without compromising the entire assembly. From a range perspective, the hybrid battery pack is impressive. Even though it's smaller than the one used in the Model 3, it can deliver between 330 and 350 miles per charge, thanks to its reduced weight and optimized aerodynamics. This result shows that efficiency isn't just about adding more cells, but about redesigning the entire vehicle to maximize available energy. It's a clear message that Tesla isn't just cutting costs, but finding new ways to do more with less. And then there's the environmental impact, a factor that increasingly weighs on purchasing decisions. Using aluminum on a larger scale means reducing pressure on lithium mines and diversifying the supply chain. Furthermore, it increases the possibility of recycling, as aluminum is one of the most reusable metals in the industry. In practical terms, the Model 2 will not only be more affordable for consumers, but will also have a more sustainable DNA from its manufacturing. To achieve such a low price without sacrificing safety or performance, Tesla had to be meticulous in its choice of materials. The Model 2 isn't made from any cheap metal alloy, but rather from a combination designed to balance cost, lightness, and strength. In the Giga castings, for example, 6000 and 7000 series aluminum alloys come into play, known for offering high mechanical strength and excellent corrosion resistance. These materials are even used in aerospace applications, which already hints at the robustness expected in this compact car. But not everything can be replaced with aluminum. In safety-critical areas, such as side protection bars or door reinforcements, Tesla uses ultra-high-strength boron steel, capable of withstanding extreme pressures in the event of a collision. This strategy of using different materials selectively and intelligently ensures that the Model 2 remains lightweight, without compromising occupant protection. It's the kind of detail that makes a difference and is typically only found in much more expensive cars. The result of this combination is a vehicle with an estimated weight of under 1,400 kilograms, about 15% lighter than models like the Nissan Leaf or Chevrolet Bolt. This weight reduction translates to greater energy efficiency, greater range with smaller batteries, and even better dynamic performance. A lighter car uses less energy to move, wears out tires and brakes less, and offers more agile handling, something drivers will certainly notice. Another key factor is aerodynamics. The Model 2 was designed to have a drag coefficient of around 0.23, an impressive figure for an entry-level car. This was achieved by eliminating elements that create turbulence, such as protruding door handles and bulky side mirrors. Instead, Tesla adopted cleaner surfaces, recessed door handles, and an aerodynamic shield that covers the entire floor. Every detail was designed to cut through the wind with minimal resistance. This obsession with efficiency isn't just aesthetic. Less drag means more miles on the same charge, without needing to increase battery size. It's a seemingly simple trick, but one that many manufacturers still neglect in cheaper vehicles. The Model 2, in this sense, proves that it's possible to deliver cutting-edge design and efficiency without raising the price to the level of premium models. In addition to aerodynamics, Tesla added layers of corrosion protection to the floor, using high-strength powder coatings. This helps preserve the car's durability in harsher climates, such as coastal regions or areas subject to road salt in winter. At the same time, the cabin features lightweight soundproofing solutions that maintain comfort without adding unnecessary weight. It's the kind of balance that makes the driver feel like they're in a more expensive car than it actually is. What really sets the Tesla Model 2 apart isn't just its affordable purchase price, but the impact it will have on consumers' wallets over the years. Tesla has estimated that the total cost of ownership over 10 years will be 30% to 40% lower than that of a similarly priced internal combustion engine. This is because the Model 2's logic is simple: fewer moving parts, less wear and tear, less maintenance. While internal combustion engines require oil, belts, filters, and constant servicing, an electric vehicle of this type virtually eliminates most of these concerns. Imagine the difference for those who depend on their cars daily. Oil changes are no longer necessary. Typical engine problems with hundreds of moving parts disappear, and even brakes last longer, as the battery's regeneration system takes over some of the work. This combination of factors drastically reduces repair visits, which means more time on the road and less money spent on repairs.